Hi there. We've been working through a lot of topics here through Calculus AB course. And whether you're taking it for the AP exam or not, these topics are going to apply. So you're going to see topics like this in pretty much a standard calculus class. So this video is going to focus on volumes of solids of revolution, a topic in every calculus class. Now, if you're taking it at the college level, sometimes this is the bridge between calculus 1 and calculus 2, depending on where you're taking the class. But in AP, this is very distinctly in calculus 1 in AB. So here's the general idea, and we've got to picture it. We're taking a region like of this shape here, and we're rotating it about an axis. When we rotate that region about an axis, we get a 3D model. We want to calculate the volume of that 3D model. And so we use a method of discs where we slice this region into paper thin discs, calculating the area of that disc. And then, much like we did with Riemann sums, where we stacked those rectangles, packed them into the area under that curve, we pack these circular discs side by side, calculating them to get our volume. Now, in order to do the sum of all of the discs, we are going to take the integral from A to B. And then I want you to notice that we're doing pi times something squared. Remember, that's the area of the circular disc. And if these discs are paper thin, then when we stack them close together, then we get the volume. Now, very importantly, we are going to take our curve minus the axis of rotation. Now, we'll start out with pretty easy ones where the axis of rotation is the x-axis. That'll make it super simple as we're trying to calculate. Then we'll look at, well, what if there's a hole in the middle? And that we sometimes call that washer method, but really it's still the disc method, just cutting out the hole that's in the middle. Friends, I neglected to introduce myself, and my name is Dr. Marissa May. I'm on a mission to help students feel confident in their math classroom. So, this video is just one of those resources. If this is the first time you're seeing my face, please make sure it's not the last by clicking that like and subscribe button. That way, you get a notification every single time a new video is posted and you won't miss out on any of those resources. Also, if you can think of a way that I can help you, if you need another resource, you need another video, you need some kind of learning guide, I'm all about that. So leave me a comment below. I'd be glad to help in any way that I can. So let's jump into, now that you kind of got the general idea of the disc method, let's take a look at how do we actually calculate that. Okay, this is a very important point. If the axis of rotation is either the x-axis or is parallel to the x-axis, then your integral is going to be in terms of x. That's important. So if you're revolving about a horizontal line, then your integral needs to be in terms of x. All right, let's take a look at this region here. It's bounded by x squared and the line x plus 2. We want to find the volume of the solid form when the region's rotated about the x-axis. So you got to think we're rotating about this region. Okay. Now, I like to tell students to recognize that there is space here between the region and the axis of rotation. When that space happens, you have a hole. You have some kind of hole inside of your disc, inside of your 3D figure. So when you do that, it's very important that we use our formula here. And I'm going to just drop it back in here, that when we have space between our region and our axis we're rotating about, then we have to cut out, we have to do what's called washer method. We have to do our outer function minus the axis, and we square that. Then we do our minus our inner function minus the axis, and we square that as well. So let's look at how can we put that together. Okay. So I want you to look at the outer function. Now, when we say outer, we're talking about outer from the axis that you're rotating about. So our outer function here is the line. So our outer function, sometimes that we call that our big radius for these circular discs. So outer function minus axis would be, that's our line, x plus 2 minus the axis, which is 0. So we get x plus 2. The inner function minus axis, sometimes we call that the small radius, is from here to here. That's the parabola. So that's our x squared minus 0. So we get x squared. So when we put this together, we'll have our volume equals pi. Now, the bounds are the bounds for the region. So it's from -1 to 2. It's the outer function minus axis squared, x plus 2, then square it. We're squaring because of the area of a circle, pi r squared, minus our inner function minus axis, that's our x squared, and we square that. And that is how we find our volume. Now we're going to do a little bit, we're going to go ahead and just multiply it out. We won't always do this, and a lot of times, I'll be honest with you, you're going to see these volumes done with calculator. This one's just a polynomial, so it's not too hard. So I'm just going to integrate there. That's 1/3 x cubed plus 2x squared plus 4x minus 1/5 x to the 5th. And we're going from -1 to 2. So let's put in the 2 first. That would be 8/3 plus 8 plus 8 minus 32/5. And then I've got minus pi, and then I'm putting in -1. That's -1/3 plus 2 minus 4 plus 1/5. And then we just have a little bit of fraction work. Okay, so just a little bit of fraction work there, and that leaves me with 2/16 pi. Okay, next let's look at what if we rotate about the line y equals 4. This one's interesting. I'm going to actually redraw the region here just as a sketch because I want you to see things are changing when we do that. So there's the parabola. There's the line. Really, I just need a sketch, right? And then I want you to see that we're rotating now about this line. So the line is now above the region. You might say, well, what difference does it make? It makes a big difference because now our outer function is different. So our outer function goes from the axis to the function, and it's the parabola this time. So that's why I almost call it the big radius or the outer function. You can do function minus axis. So that's parabola minus the line, and we're going to square it, okay? And then the little radius, or that would be the inside function minus the axis. So that would be our x plus 2 minus 4, and then we have to square that. So when we put this integral together, now the region, the bounds never change. So that's, or didn't change in this case because we didn't change the region that we were rotating. So now we've got x squared minus 4 minus x minus 2 squared dx. And let me do the antiderivatives for, I'll multiply it out and I'll do the antiderivative. Okay, so there's my multiplied out part and I simplified it. Now let's get the antiderivative. And then let's plug in our values of 2 and 1, -1, and let's see what we get for our volume. I get 108/5 pi. when I plug those values in. Okay, the last one we want to look at is, let's take the same region, but this time let's revolve about the line y equals -2, which would be down here. Again, we get a little bit different take because the region's not moving, but the axis that we're rotating about is definitely moving. And we're rotating about this line down here. Okay, so I'm going to point out our big radius is from the axis of rotation to the furthest curve away, which is the line in this case. And then our smaller radius comes from the axis we're rotating to the curve that's the closest. And that's the parabola in this case. Okay, so my big radius is my outer function, that's the line, x plus 2, minus my axis. So it's minus -2, which would be just x plus 4. My little radius is my inside function, that's my parabola, minus -2, or that would just be x squared plus 2. So when we write our integral this time, we've got pi times the integral from -1 to 2. My big radius is x plus 4, and I'm squaring it. My little radius is x squared plus 2, and I'm squaring that. Okay, so let's expand that. And then we'll collect our like terms and take the antiderivative. See, negative x to the 4th minus 3x squared plus 8x plus 12 dx. Then I'm going to take the antiderivative. So I got -1/5 minus x cubed plus 4x squared plus 12x. And we're going from -1 to 2. I'm sorry, -1/5 x to the 5th. Okay, let's plug in the 2 and then the -1. So I end up with 159 pi by plugging in my -1, plugging in my 2. Okay, so really, really practice with where that axis of rotation is. You need your big radius, and you need your smaller radius. Um, at the order which you subtract really doesn't matter because you're going to square them inside of the integral anyways. So don't get caught up on that. I don't want that to hold you back. Let's take a look then when your axis of rotation is parallel to the y-axis. So in this case, then you need to have your integrals be in terms of y. You're still going to do your big radius and your small radius. You're just going to have to do them in terms of y. So we're going to rotate this region about the y-axis now. I think it's beneficial to go ahead and solve your equations for y, just so you have, I'm sorry, solve them for x, just so you have them. So like this one here, I would go ahead and square both sides. And then this one here, I would add 2 to both sides. Okay. Now I'm going to I'm going about the y-axis. And so I have a big radius and a small radius. My big radius comes from my axis of rotation to the furthest curve away. That's the line. And my small radius comes from the axis of rotation to the closest curve, which would be the parabola there. Okay, so my big radius is the line y plus 2 minus the axis, which is 0. My small radius would be the parabola minus the axis. Oops, and I put x squared. So y squared minus 0, or just y squared. So let's write the integral. My bounds, remember, my bounds also have to be in terms of y. So they're going from -1 to 2, although they are similar to the last problem example we did. The reasons are different. So we got big radius, which is y plus 2 squared, minus small radius, which is y squared. Remember, we're squaring both of them. We're making sure we have dy's, and let's integrate. Now, the integration here actually plays out the exact same way the previous one did because, I mean, the only thing that changed was that our integral changed. So you should get 216 pi. And then let's go ahead and we're going to revolve about the line x equals 4. So that's over here. I'm going to draw it on the same graph. Okay. But I'm going to highlight where we get our radius from. So we do have 2 radii here. So the big one comes from the axis of rotation to the furthest curve away. That is the parabola. The small radius comes from the axis of rotation to the closest curve. That's the line. So in this one, you have your big radius is the parabola minus the axis, which is 4. Your small radius is your line, y plus 2, minus the axis, which gives you y minus 2. Now, when we write that integral, we're still going from -1 to 2. We've got our big radius squared minus our small radius squared dy. And let's go ahead and again, we just did this, so we know that we should get the same answer as before. Now, we're getting the same answer because we're using very similar curves. This doesn't always happen, but you definitely can practice by multiplying it out, doing your antiderivatives, and so forth. Okay, then let's do one more. That's where we're going to go about the line y equals 7. So that is I'm sorry, that's not y equals 7. That's x equals 7. So it's way out here. Okay. So again, we're going from the axis of rotation all the way to the furthest curve. That's my big radius, which in this case is the parabola. So my big radius is the parabola minus 7. I think I'm running out of ink there. And then my small radius, again, from the axis of rotation to the closest curve, that's the line. So my little radius, you'll see some textbooks write this as big R and little r. That's why I'm picking up on that. And now we can write our integral. Okay. So I'm going from -1 to 2, big radius minus small radius squared and dy. Now, here's a pro tip for you. If you're going to use a calculator, I would definitely encourage you to put the integral in without the pi. That's going to allow you to get a fraction that you can stick the pi on. If you put the pi in the calculator with the integral, the calculator will never be able to give you a fraction back. So type the integral in separately, then tag the pi on your answer. That's going to make things a lot simpler. Let me switch our view to show you how I put this in Desmos. So if you can see, I didn't put the pi here because I wanted to get a nice answer. So you can actually write your answer here as 48.6 pi, or you can use the little fraction button over here on Desmos, and Desmos will give you the fraction for that, 243 fifths, and then you can put the pi on it. So either way works, but definitely leave the pi off when you use the graphing calculator so that you can get that nicer answer, and then stick your pi on. So I hope this helps. One of the great topics. I'm going to do another video of volumes with practice problems, and then I'll also do another video of volumes with cross section. So I'll be sure and link those below. That way you get you can access those if you need some more help with volumes. Don't forget to hit the like and subscribe button and leave me a comment if you need some more help. Thanks so much. Bye bye.